AP Calculus AB, Unit 9, Day 7, lesson. We're going to go a little more into area. We've been using area, talking about area this unit, but we're going to take it to take it up a step. So, we've been talking about this idea that when we integrate, we're getting area. And the idea is that we're slicing it up into thin slices, okay, and accumulating them. And we can look at one single slice as like a thin rectangle. Okay, one single slice. The height of the rectangle is the y value, the function value. So each very thin slice, infinitely thin slice, has an area. The thickness we're going to call dx, which is like a very small change in x. So when you integrate here, this is like the height of your rectangle, and this is like the base of your rectangle. And that gives you the area of a single rectangle. And then we accumulate all of them to get the area. Now, it's not really area, it's signed area, remember, because it could come out negative, right? But we're accumulating all of these thin rectangles and adding them together, okay? This is actually the way your calculator does it. Your graphing calculator, they don't know the antiderivatives. And they can integrate things that we can't integrate. And they actually do these very, very thin. They make the thickness 0.001, which maybe doesn't seem that thin, but it gives a pretty good answer. When we do them exactly, we are taking dx to 0. If the function is positive, then the area between the function and the x-axis will be this. So this is just saying, well, if the function is above the x-axis, it actually is area. Because today, while we've been associating integrals with area, we've never really been asking to find the area of like a shape on a picture. We've just been using the area to help us find integrals. But now today we're going to actually talk about trying to find area. So going back to just a simple example, here's a function. It's a parabola. And let's say we want the area, the integral from 3 to 6. And so the way we would do this exactly is we'd say, all right, let's integrate x squared from 3 to 6. The antiderivative is x cubed. We don't need to put the plus c, even though it technically is there. If you plug 6 in here, you get 72. You plug 3 in here, you get 9. So the answer is 63. Remember, when you plug 6 in, it's like you find the area from 0 to 6, and 3 in, 0 to 3. And so that's why we always subtract the second smaller one from the big one, because it gives you the difference in between, which is what we're going for. So here's the deal. We're now going to involve multiple curves, okay? Intersecting curves, and we're going to try and find the area between those curves. So here's a simple example. We have a parabola, like the one we were just doing, and then we have a square root function, which is the top half of a sideways parabola. Now, we want to find the area in between these, okay? And the way we're going to do that is we're going to find the area under the bigger function, and then we're going to find the area for the function underneath it, and then we're going to subtract to get what's in between. So this is a common geometric strategy. Now, one of the things that we need to know is we've got to figure out where to start and end our integration. And those are going to be the intersection points. So we got to get the intersection points. And so we're going to have to do a little algebra for that. We're going to have to set one function equal to the other function and then solve. So here, you'd square both sides. X to the fourth equals x. Move everything on one side equals 0. Factor it. Say each factor equal to 0. We get x cubed equals 1. We take the cube root of both sides. No plus or minus, it's an odd root. We get x equals 1. So this is this guy right here. If you want the y coordinate, you plug it in here, you get 0. The 1 is right here. And if you want the y coordinate, you plug 1 into either function, and you get the y value. So that's a big deal. So now when we go to find the area between these curves, we want to integrate left to right 0 to 1 of the higher function, which is the square root function, and then integrate 0 to 1 of the lower function, x squared dx. And this should give us the area in between them. This should give us the area underneath that curve by itself. This should give us the area in between underneath that curve by itself. And then if we subtract that, subtract this from the whole thing, we should get what's left inside in between. So that's how we're going to do it. This is x to the 1/2 power. So this is x to the 3/2. Divide by the new exponent. Go to 1. This is going to be x cubed over 3. 0 to 1. So we're going to get 2/3 minus 0. This one can get 1/3 minus 0. And so the area under the high curve is 2/3. The area under the low curve is 1/3. And the difference between them is 1/3. And that is the area between those two curves. So that's our general strategy for dealing with, two curves. Now, we could write this down, this strategy. This is not a formula to memorize for sure. It's more of a basic idea, high curve minus low curve. But we could kind of write that down. It could be, now we could do the y top curve dx minus y bottom curve dx. The limits are going to be left to right. It's going to be x left to x right. This is going to be x left to x right, and they're the same limit. So one of the cool things that we could do is we could really just combine them into the same function and kind of think, well, the height of these slices in between, we could just do slices of the in-between area and just say, let's accumulate all those. And so the height of these slices would be the y value of this curve minus y value of this curve. It's kind of a different thought process. You do y top minus y bottom inside a single integral to get the height of a single slice of the in-between area and just do a single integral. The work is about the same by hand. So, and by the way, properties of definite integrals say that you can do that too, right? So either way you want to do it. Now, what if the functions are below the x-axis? We are literally looking for area. It has to come out positive. It cannot come out negative anymore. So if both functions are below the x-axis, you still want to just do top minus bottom. You want to do f of x dx minus gx. You want to do the higher curve minus the lower curve, no matter what. If you do that, just as an example, we could say, okay, what if the coordinates of this was like 4, -2, and the coordinate of this was like 4, -8? If you were to do the top curve, -2, minus the y value of the bottom curve, you would get positive 6. It's going to give you a positive height for your rectangles. You're going to get a positive answer, even if they're both negative. Even if one's positive, one's negative, it's still going to work. I could illustrate it just with a pair of points. If you do top minus bottom, you're always going to get a positive measurement, and your integral will come out positive. So this is our general technique. Top minus bottom. Y top minus y bottom. Now, I think that should hopefully seem okay, but let's make things really interesting now. We've always been integrating with respect to x, but let's talk about integrating with respect to y. So far, we've been integrating with respect to x, and what that means is that we get vertical slices, right? The thickness of the slices are dx. We're integrating with respect to x. And maybe you didn't even ever think that we could do anything else. But with y, we're going to find the same areas, but now the slices are going to be horizontal. Okay, it's the same idea. They're all thin rectangles, but they're sideways now. Their thickness is now dy instead of dx. It's a small change in y. The dimension here is going to be x right minus x left. So if we look at one slice, we want to do the x coordinate on the right minus the x coordinate on the left to give us the dimension of that slice. So we're going to do x right, and we could do this in separate. We could find, if you integrate with respect to y, now you're going to get the area between the curve and the y-axis instead, which is kind of interesting. It's a different answer than the other way. And you're also going to integrate from bottom to top. So you're going to go y bottom to y top. And then you're going to find the area between this curve and the y-axis, which will be different than that curve and the x-axis. And you want to do the left one second, subtract it, because that's going to be a smaller area. Now, of course, we could combine these together, which I think makes a lot of sense. And think of it more like what we're drawing right here is just a single slice between the curves. And the dimension of that slice is x right minus x left. And the vertical dimension, the height, is dy. So either way you want to do it, you can split them up, you can bring them together. So for this particular problem, now there's some challenges here. We got to get the x coordinate in terms of y because we're going to integrate with respect to y. So this x coordinate right here, if you want to get x by itself, it's going to be positive square root of y. Now the negative would be the left side of the parabola, by the way. Okay, positive square root of y. I showed plus or minus. This one over here, to get x by itself, is going to be x equals y squared. That's going to be your x left. So if we're going to do this problem, y bottom is 0, y top is the y coordinate here, which is 1. And we could do x right, which is the positive square root of y, minus x left, which is y squared. And we're going to integrate with respect to y. This is going to take a while to get used to. So that's going to be y to the 1 half. That's going to be y to the 3 halves divided by the new exponent 2/3 minus y cubed over 3. I'm going to plug limits in. We're going to get 2/3 minus 1/3 minus 0 minus 0. And the answer comes out to 1/3, which, by the way, is the same answer that we got on the front for the same curves. But we sliced those ones vertically, right? You should get the same area. We're just trying to find it in a different way. Okay. Now, here's a slightly more complicated one. This one has 3 curves. It doesn't have to just be 2 curves. Now, you're only going to ever really work with 2 curves at a time. Okay. So, which way is easier, dx or dy? Most of us are going to feel more comfortable with dx right now, but dy is going to have its advantages, and sometimes it's going to be your only option. So you're not going to be able to just always do dx. So let's start the dx first. If you're doing dx, you're doing vertical slices, right? So you're going to have to find this area first and then find this area next, because the top curve and the bottom curve that create that area are different. So that's a new thing. Now, of course, we have to find the intersection points. And these intersection points are going to be, we're going to have to do the work for either way we're slicing it. So we can only do 2 curves at a time. So this intersection is between that curve and this curve. And this one's pretty easy. So that x coordinate is 1. If you want the y value, plug it into any of these functions. That square root of 1 is 1. This is just a flat line. We got to do this one up here is going to be the square root of x, and this line negative x plus 6. So I would square both sides. Isolate the radical, which it already is, x squared minus 12x plus 36. Move everything to one side, x squared minus 13x plus 36. Solve it, factor it. It's going to be minus 4 minus 9. So we're going to get x equals 4 and x equals 9. Which one is this? 4 or 9? Now, here's the thing. This is giving you two answers because it's thinking that the bottom of this sideways parabola is also there, because that would be negative square root of x, which is you'd get the same work if you squared the negative, it would give you positive x, right? And so this line, you could also imagine, will intersect it down here. This is the 9. We want the 4. Now, if you plug 4 in here, square root of 4 is 2, right? Or you plug 4 in here, you get y equals 2. You got this intersection right here to find also, and that's going to be where these two lines intersect. So you set them equal, and you get x equals 5. So you got to find the intersections, and I'd find the y values at the same time. So we did that. Now, to find this area, we're going to have to do top, y top. If you look at one slice, it's y top minus y bottom. And y top is square root of x. Y bottom is 1. And we're going to integrate with respect to x, and we're going to go left to right from 1 to 4. That's going to give you that area. And the next area is going to be 4 to 5. Y top. If you do a little, you can even draw little slices, which I highly recommend. Y top minus y bottom, because these things are going to get more complicated. So if you can practice these things now, it's going to pay off. Y top is negative 6. Y bottom is 1. So this is the setup. If we can just finish this work, it should give us that area. Now, by the way, this is also triangle, so you could do 1/2 base sum tight. There's other ways you could attack this. You could find the area under this and the area under this, and then subtract this big rectangle from it afterwards. But this is kind of more straightforward approach. So this is going to be x to 3/2, divided by the new exponent, 2/3 minus x, 1 to 4. It's going to be negative x squared over 2. That's going to be 5x. So I think there's some benefits to combine them in the same integrals. So this is going to be 2/3, 4 to 3/2, that's 4, that's 2/3, 1 to 3/2, that's 1. Minus, plus, you plug 5 in here, it's negative 25 over 2 plus 25. Minus plug 4 in, you get negative 16 over 2 is negative 8 plus 20. Bit tedious. We're going to try it with horizontal slice in a second and see if there's any benefit to it. Square root of 4 is 2, cubed is 8. This is 16/3 minus 4 minus 2/3 plus 1. This right here is that area, that first chunk of area. So we end up getting what, 14/3 minus 3, least common denominator. It's going to be 5/3. That's the area of the first chunk. Okay. Then the next one, this is going to be positive 25/2 plus 8 minus 20. So it's going to be negative 12, negative 24. It's going to be positive 1/2. Right? And the least common denominator would be 6. You get 10 plus 3 is 13 over 6, or 2 1/6. So that's the answer. That's the area between those three curves. Okay, so that's one way we do it. Let's keep an open mind. It's going to take a while before you feel really comfortable with this horizontal slicing idea. But let's take a look at the same problem. I think it's going to be worthwhile to draw a new picture. Right? Same problem. Same intersection points. We don't need to redo any of that work. But we're going to do horizontal slices. Now check it out. The benefit of the horizontal slices is that it's always the same x right minus x left. You don't have to break it up. You don't have to like change strategies. Do this minus this, and then this minus this. It's just one integral. Okay? Now we do need to get this x in terms of y. So that would be, if you were to solve for x here, that would be 6 minus y, right? And we got to get this x in terms of y, which would be y squared. So, I mean, there's that little extra work. But now it's going to be x right minus x left. And x right is 6 minus y, and x left is y squared. We're going to integrate with respect to y. Our limits are bottom to top, so the lowest y coordinate is 1, the highest y coordinate is 2. This right here is going to give us the same answer as all of that right there. And by the way, that had harder antiderivatives, I think. I feel like these antiderivatives are going to be easier. It's going to be 6y minus y squared over 2 minus y cubed over 3. And then we're going to plug in 2. We're going to get 12 minus 2 minus 8 thirds. And then we're going to plug in 1. 6 minus 1 half minus 1 third. And so we're going to get 10 negative 8 thirds plus, that's going to be negative 7 thirds, minus 6 plus 1 half. So it's going to be 4 minus 7 thirds. Now I'm just trying to get through these numbers here. Least common denominator, 6. So it's going to be 24 minus 14 is 10, plus 3 is 13 over 6. Now, I'm not saying that was easy, but I feel like this was a lot simpler than that. I mean, and it was just cleaner. So I'm just telling you, there will be times where horizontal slicing is going to be a lot easier than vertical slicing. And then also, there's going to be times where you have to do it with horizontal slicing. It's not even a choice. So we got the same answer, but this is pretty much the last thing from this unit that you need to start working on. And it's going to take a while to get used to this horizontal slicing idea, but it's going to pay off and just easier work. But also, there's going to be problems where you have to do it with horizontal slicing. Same ideas. It's a little weird because you've never even considered it. You're just used to the other way, and you just don't even think of it. So try the assignment, worksheet 9.7.